Okay, let's begin the discussion of chemical reactions, which we symbolize using chemical equations. Remember that chemical reactions involve the rearrangement of atoms, that atoms at the kinds of temperatures and energies we deal with here on Earth are intact in chemical reactions. The nuclei come through unscathed. So the number of atoms of each kind must be the same on both sides of a chemical equation. That's a statement of the conservation of matter, which for chemical reactions is obeyed. So we can start with the simple case of burning carbon. When carbon burns in excess oxygen, the product is carbon dioxide. We can symbolize that on the microscopic or submicroscopic level as follows. You have here one carbon atom, and it's reacting with two oxygen atoms in the form of an oxygen molecule to form carbon dioxide, which is a molecular compound. You can see that there's one carbon atom on the left and one on the right. You can see that there are two oxygen atoms in the form of an oxygen molecule on the left and two on the right. So this represents a balanced equation already. And to write this symbolically, we write the element's symbol followed by the state in which we find it. Solid, liquid, gas, or if it's dissolved in water, the state is called aqueous or AQ. Carbon, as you know, is a solid at room temperature. If you use charcoal to cook on an outdoor grill, you would be using essentially carbon. Carbon's also what's in a lead pencil, even though we call it lead. It's actually graphite, which is a form of carbon. So we take solid carbon and we react it with oxygen in the atmosphere, which is O2, and of course it's a gas. Remember, oxygen and nitrogen, the two dominant gases in the atmosphere, are both diatomic in their elemental form. And the product of this is the molecule carbon dioxide, CO2. Now this is important. Anytime you burn carbon or a carbon-containing compound, one of the products will be carbon dioxide, unless you burn in limited oxygen, in which case you can make another product, a very deadly product, called carbon monoxide. Carbon monoxide forms when there's limited oxygen, and the microscopic picture of how that would work is as follows. Now here we see that we have, again, the submicroscopic symbol of carbon, diatomic oxygen, and now the product is carbon monoxide, CO. Now, as you know, carbon monoxide is a deadly poison. Unlike carbon dioxide, obviously carbon dioxide is having dire consequences on the environment, but it's not a deadly poison the way carbon monoxide is. And the reason for that is, and I think you can see this in the symbolism here, carbon monoxide looks to hemoglobin as if it's oxygen. Now, as you know, hemoglobin carries oxygen from the lungs to cells throughout the body, to which it releases the oxygen and then picks up carbon dioxide, the byproduct of respiration, carries the carbon dioxide to the lungs, and then you exhale the CO2. Carbon monoxide attaches to the same active site that carbon dioxide does, but it doesn't let go. So once carbon monoxide attaches to the active site, the heme molecule is no longer able to transport oxygen, and if enough of your heme molecules are compromised in this way, you suffocate. So carbon monoxide is a deadly gas that's produced anytime, actually, that you burn a hydrocarbon or carbon, unless oxygen is in large excess. This is why it's so dangerous to use a gas grill or anything burning charcoal indoors, because you're always going to produce carbon monoxide. Now, we see here that we still have one carbon atom on both sides, but this time there's only one oxygen on the right, whereas there are two on the left. To balance this, I cannot add another oxygen to the CO, because that would make it a different molecule, carbon dioxide, the one we saw in the previous example. What I can do instead is form two of them, which solves my oxygen problem. With two carbon dioxide molecules, I have two oxygens, just as I have with one oxygen molecule. However, the carbon is no longer balanced, so I'll need two of those. So this time, the symbolic representation of the combustion of carbon to form carbon monoxide is going to require two carbon atoms, and they're both solid, plus O2, to form two CO gas. Notice now I'm using coefficients to provide the extra atoms necessary to balance the equation. Okay, next let's look at the first of the hydrocarbons that we're going to be visiting in this class, the chemical reaction of methane, the simplest hydrocarbon, with oxygen to form carbon dioxide and water. Now, this is called combustion. Any reaction with oxygen is called combustion because oxygen reactions are so ubiquitous on Earth. Methane, the simplest hydrocarbon, is CH4. A hydrocarbon, as the name implies, is a molecule that contains only carbon and hydrogen, though sometimes we slip up and call alcohols hydrocarbons, even though they also contain oxygen in addition to carbon and hydrogen. We will be considering hydrocarbons as a class, partly because our society relies on them so heavily for our energy. So we see here that like all hydrocarbon combustions, the products are carbon dioxide and water, and a good rule of thumb when you're balancing combustion reactions of hydrocarbons is to leave the oxygen till last, because oxygen contains only one kind of atom. That way, if you change the coefficient for the O2, all you change is oxygen. If you change any of the other coefficients, you're going to change two things. If we start by balancing carbon, which is generally a good way to start, we can see that carbon's already balanced in this example. On the other hand, hydrogen is not. Methane on the left-hand side contains 4 hydrogens, and on the right-hand side, water only contains 2. So I'm going to need a second water molecule to balance the hydrogens. Now I've got 4 hydrogens on the left and 4 hydrogens on the right. The carbon is still balanced, so all I'll need to do is balance the oxygens. There's now 4 oxygens on the right-hand side, 2 in the water, 2 more in the carbon dioxide, 1 on the left, so we need a second oxygen. And this represents the balanced equation of the reaction of methane, the simplest hydrocarbon, with oxygen to form carbon dioxide and water. Again, the general rule is that hydrocarbons burn to form carbon dioxide and water, and you will need to be able to complete and balance hydrocarbon combustion reactions by adding the CO2 and water and then balancing the resulting equation. So in this equation, symbolically, we have CH4. Turns out that methane and many of the other smaller hydrocarbons are gases at room temperature. We would need to tell you that. You're going to need 2 oxygens. Again, diatomic oxygen, that you should know. We get CO2, which is a gas. And we're going to make water liquid in this case. Clearly, if you burn methane, the temperature gets hot enough to make gaseous water or water vapor. But in chemistry, we often consider reactions occurring at 25 degrees. And at 25 degrees, water is a liquid. In any case, you would be given information about phases of species that you're not expected to know. That is, you wouldn't know necessarily that water was a liquid under these conditions. But you should know that oxygen is a diatomic gaseous molecule, and so is CO2. All right. 2 broad categories of chemical reactions that we'll be considering here are combination reactions, and I'm using combination reactions to do an example of what is another class of chemical reactions that we expect you to be able to complete and balance. This is in addition to the hydrocarbon combustion reactions. So here we have the reaction of a metal, iron, with the nonmetal oxygen. Now, as you know, metals tend to lose electrons to get more stable, to form the cation, whereas nonmetals like oxygen gain electrons to get the same configuration as the nearest noble gas. In this case, the nearest noble gas to oxygen is neon. So iron wants to lose, oxygen wants to gain, and like most of the metal-nonmetal reactions, the result is an ionic compound. So we start with iron, which is Fe, and it's a solid at room temperature. We combine it with oxygen, the diatomic gas, and the product here would be hard for you to predict because iron, as a transition metal, can form 2 different ions, the +2 and the +3. It turns out that the product of the combustion with oxygen is the +3 ion, so you make Fe2O3, and that's a solid. Fe2O3, by the way, is rust. In general, though, if you have a metal and a nonmetal reacting, the product will be the ionic compound you would predict when you look at the ions that would form from the metal and the nonmetal. If, for example, we had reacted magnesium, which is also a solid, with oxygen, as you can see from the periodic table, magnesium is in group 2A. It's an alkaline earth metal, and therefore it only forms the +2 cation. Oxygen in group 6A only forms the -2 ion under normal circumstances. So since magnesium forms +2 and oxygen forms -2, the product must be MgO, which is a solid. So you can predict the formula for the ionic compound if you know the charges of the ions that are formed when a metal forming the cation combines with a nonmetal forming the anion. Now, neither of these equations are balanced. You could leave oxygen till last, but since iron or magnesium is by itself, let's leave it until last. To balance the first equation, you see that in order to balance the oxygen, we have 3 on the right and 2 on the left. That must mean that we have a common denominator of 6, requiring 3 oxygen molecules and 2 Fe2O3s to balance. That puts the Fe total to 4 on the right, so we're going to need 4 on the left. As far as the magnesium-oxygen reaction is concerned, you can see we're going to need 2 MgO to balance the oxygens, which means we need 2 Mg to finish.